In this video, we are going to talk about constrained motion in two dimension. Let us take a frame of reference with x-axis horizontal and y-axis vertical, and we have a trajectory y equal to fx along which a particle is moving. So it is termed as constrained motion, in a sense that the particle is constrained to move along this curve only, and we have drawn a tangent pt to that curve at the locus point P. So the framework is more or less following basic Newtonian dynamics. The weight of the particle of mass m acts vertically downwards. If we take the mass m to be known, then we may put it as mg. We prefer to take m as 1, and the gravitational pull is acting on the particle downwards. This angle psi which the tangent makes with x-axis is obviously given by tan psi equal to dy dx. Now, as far as the tangential acceleration and normal acceleration along the tangent and along the normal is concerned, we know that one is v dv ds and another is v square by rho. And the reaction of this path upon the particle, it also acts along the same perpendicular to the tangent, and we put it as r. So the equation of motion in case of a particle crawling upwards against the gravity with initial velocity, say v0, and we may assume that the initial starting point p0 is at such a point where the tangent makes an angle 0 with the x-axis, isn't it so? So the initial condition is v0 at t equal to t0 and psi equal to psi 0. So this is the framework, and we can easily see that since this is psi and this is 90 degrees, so this is 90 minus psi, and the component of g along this tangent becomes g sin psi, while the component perpendicular to the tangent becomes g cos psi, because this is psi and this is 90 minus psi. And x being horizontal, the vertical pull g acts perpendicular to it, so this is 90 degree. So obviously v dv ds becomes clearly becomes minus g sin psi, and if we take the curve to be rough, not smooth, then since the reaction is r, a dragging force mu r acts opposite to the motion along the curve upwards. So this is minus g sin psi minus mu r. And resolving the components perpendicular to the tangent, we get that v square by rho is nothing but r minus g cos psi. And these two equations, sorry, I should adjust a bit so it's visible, I think. Clear? I'm very sorry. So v dv ds, let me repeat it, v dv ds is the tangential acceleration, that is equal to minus g sin psi and minus mu r. Both the forces are dragging the particle downwards, but the particle is climbing upwards due to this initial velocity starting from p0 at time t0, where psi is equal to psi 0, which is actually 0, because we have assumed that at P0 the tangent is parallel to x-axis. So from these two equations we may easily write that v dv ds plus mu v square by rho is equal to minus g sin psi plus mu cos psi. Isn't it so? We have multiplied mu with this equation and added it to the, so that this mu cancels out, and we have minus g sin psi plus mu cos psi on the right hand side, and in the left hand side we have v dv ds plus mu v square by rho. Now let me wipe out the figure and concentrate on this. The geometry is quite clear, and we have this equation, which is nothing but, let me write it again like this. I have applied chain rule here, v dv d psi into d psi ds, obviously for a specific purpose, plus mu v square by rho is equal to minus g sin psi plus mu cos psi. Okay, and since this rho is defined to be the radius of curvature and s is the arc length, we all know that d psi ds is nothing but 1 by rho. This is a formula or definition of radius of curvature. This is nothing but ds d psi. D psi ds is the measurement of curvature, and radius of curvature is the reciprocal of curvature, which turns out to be nothing but ds d psi, and so we can replace it by 1 by rho. And once we replace this 1 by rho, we can take this 2 rho common, so that rho is multiplied here, and this can be written as d psi of v square by 2, and this can be written as 2 mu v square by 2, and we have minus rho into g sin psi plus mu cos psi. Okay, so this is a linear differential equation which has integrating factor e to the power 2 mu psi. Isn't it so? If we take v square by 2 to be the dependent variable and psi to be the independent variable, this is nothing but dz d psi plus 2 mu z equal to some function of psi. Rho is also a function of psi, and integrating factor of this equation is e to the power 2 mu psi. So we have v square by 2 e to the power 2 mu psi is equal to minus rho g sin psi plus mu cos psi. Okay, so that is the solution of v square. We may easily integrate this right hand side and get the value of v square with this initial condition. What is the initial condition? The initial condition is nothing but v equal to v0 at psi equal to 0. Since we have assumed that the P0 point from which the particle starts has the tangent parallel to x-axis. Isn't it so? While climbing down, the equation of motion changes. let us retract to the figure again. This was the curve. We have drawn a tangent. This was the frame of reference where x-axis is horizontal and y-axis is vertical. The weight of the particle at the point Pxy, locus point of the curve y equal to fx, acts downwards, and we assume tan psi divide x. That is, we have assumed that the tangent at P makes an angle psi with the x-axis. Now, if this is the initial position of the particle and it moves down with zero velocity, that is from rest, it starts moving downwards for the gravitational pull, then the equation of motion obviously changed. Equation of motion for particle moving down the curve under gravity. Obviously, the curve is rough curve. So, this is the R reaction, and since it is crawling downwards, mu R will act opposing the motion. VdVds is acting downwards, and since this is psi and this is 90 minus psi, g sin psi and g cos psi will be the components along the tangent and along the normal. So, we have as equation of motion in case of downward motion, VdVds is equal to g sin psi minus mu r, because mu r is opposing, and we have v square by rho equal to r minus g cos psi. And from these two, in a similar fashion, we may find that v dvds plus mu v square by rho, we have added these two so that mu r cancels out, and we have in the right hand side as g into sin psi minus mu cos psi. Isn't it so? It's clear from these two. It's clear from these two. From these two equations, it's clear that v dvds plus mu v square by rho is g into sin psi minus mu cos psi. So, we may write this equation as again v dv d psi into d psi ds plus mu v square by rho is equal to g sin psi minus mu cos psi, and as d psi ds is again 1 by rho and v dv d psi may easily be written as v square by 2, we have again a linear equation which has the integrating factor e to the power 2 mu psi, and when we multiply with e to the power 2 mu psi both sides, we get v square by 2 e to the power 2 mu psi is equal to 0 sin psi minus mu cos psi e to the power 2 mu psi d psi. Then one can easily have the value of v square as 2 e to the power minus 2 mu psi into, say that we have assumed here that rho is not a function of psi, or we have a constant radius of curvature. But in case of general discussion, we should keep the rho within the integral sign, isn't it so? Because rho may be a function of psi. For constant radius, that means for a circle or for any curve which has radius of curvature not dependent on psi or constant curvature, we may keep it outside. So this is g into, and if we integrate this, we have some function of psi, and we will have to adjust with a constant, isn't it so, of integration. K is the constant of integration, and that can be easily found from the initial condition. Which is the initial condition? The initial condition is that at time t equal to 0, we have psi equal to pi by 2 and v equal to 0. So you put these values here and get the respective value of the constant of integration, and that is how we get the expression of velocity in case of constrained motion moving downwards under gravity.